Hello, my name is Chieh, and welcome to my presentation on deep layerwise networks have closed form weights. This is a paper that was recently accepted for AIStat 2022. So we all know that today neural networks are optimized essentially using backpropagation. And here has triggered essentially a debate to see if the brain maybe is also doing backpropagation. And of course, it's a debate. Therefore, some people says, yeah, it's possible, and others says, no, that's not possible. And because of this debate, it has essentially inspired a search for alternative optimization strategies, so that it's without backpropagation. So it's less controversial approach. And this essentially led to layer-wise training. And the way it works with layer-wise training is pretty easy. Essentially, you pretend that it's just one layer, and you train the weight here with gradient descent or something. And then once you have the weights, you add a new layer, and then you hold this weight constant and just train this one. And then so on and so forth as you add more and more layers. So this general approach bypasses backpropagation and is less controversial. And it has some pretty promising results so far, showing that it can give you good results. However, there's some theoretical questions that still remains. For example, well, if we're talking about the brain, we still have to compute gradients, for example, to optimize each layer. Can we even bypass gradient-based optimization? In fact, can we do something even simpler? Can we just use some very basic closed form solution, and by repeating it over and over again at each layer, it will automatically optimize the network, right? This was inspired by nature, where we noticed that very simple patterns, if you repeat them iteratively, it actually becomes something very complicated, like a fractal or a tree, right? So, so this was the first theoretical question we had. Is the closed form solution even theoretically possible? Is that even possible? And the second question is, since we're adding network layer after layer, how do we know when to stop, right? And with neural network today, which essentially has the same question, how deep should the network be? And we wanted to essentially have some theoretical results on identifying the network depth. So our contribution is that first, we discover a closed form solution, that it does exist and is theoretically possible. That by using this like simple weight, just stack them together, the network automatically optimizes to approach the global optimum of the classification objective. And second, it turns out that this closed form weight is just the kernel mean embedding under our construct. And the second contribution is that we discover a strategy to essentially identify the appropriate network depth, right? We propose that maybe if we add more and more layers, and if we look at the network as a function, it gets to a point where you add a network that the network at Fn and Fn plus 1, when you add this extra layer, they're essentially the same. So the idea is that, well, maybe it gets to a point that the network converges. And when it converges, it doesn't matter if you add more layer anymore. And what we discover is that it does. Yes, this actually converges to a kernel when you add more and more layers. And this kernel is what we call a neural indicator kernel. So the key idea of our approach is very simple. It's heavily based on this notation. So you will have to understand this notation first. What we do is we imagine there's just one layer. We train this layer. And then we now have two layers. So in the beginning, this layer is just a function. But when it gets to two layers, it's actually a composition of function 1 and function 2. And we denote this with a composition symbol. This implies that it's 1 and 2 together. And this implies that it's 1, 2, 3 together. Okay? So what we're training is actually a sequence of functions. We first train this one, then we train this one, then we train this one, and so on and so forth. We're going to call this sequence of functions as a kernel sequence. Okay? Now, if we plug this into the objective at every single stage, we're going to get a yet another sequence of objectives. So what we're doing is we're minimizing this objective, then this one, and all the way to the alpha layer. So we're going to call this the risk sequence, or the H sequence, since we use the symbol H. So the risk, we're constantly solving a different risk. And the general strategy that we'll use is that we're going to pick some closed form weight. Once we have this weight, it allows us to generate a kernel sequence. We want to find a weight such that the risk sequence here is automatically pushed towards its global optimal, implying that just by using this weight and essentially grind through this process, this objective is automatically optimized. That's the general strategy. So how do we pick the empirical risk? Right? Here, this is actually a very generic empirical risk, but what is the actual loss function here? Okay? And when we are deciding which loss function to use, we notice a couple things. So for classification, we notice that if we have a mapping, we found a solution such that the label give us 0 and 1 between two classes, instead of the true label, -1 and 1, it doesn't really matter. We're going to get the same classification anyways. In fact, it doesn't really matter. It could be 10 and 23, and we can still distinguish the two classes apart, right? As long as this and this doesn't equal to each other, that's all that's necessary. And therefore, enforcing that the function that we find is equal to the label actually doesn't make sense for classification. It's kind of unnecessarily strong constraint. And we posit that if we relax this constraint, maybe it will be easier during optimization. And therefore, instead of like mean square and cross entropy, we decided to use an objective that really just focus on the core necessity of classification, which is learning a mapping where similar in different classes becomes easily distinguishable, right? That's all you care, is that there's a mapping. Once you map it, you know that this is class A, that's class B. That's all that matters. But here comes the complexity. Well, similarity is a very, very elusive concept. Like different data sets have different ideas of similarity. So how do you know how to pick the similarity, right? How do you define similarity, right? Does that imply every single data set you need to use a different similarity? So we discover that when you use the Hilbert-Schmidt independence criterion, or AIStats, for this situation, it's actually very, very ideal. So let me explain the objective to you. The objective here is that you have the input to a layer. So R here is a set of data, but it's just one data for lowercase r. What you do is you multiply by the weight, so R times the weight, and then you pass it through an activation function. So this right here is the output. So the idea of AIStats is that you take the output and you try to maximize the dependency between the layer output and just the label. So gamma here, you can imagine as just a label. So this right here is another way of writing essentially correlation. So you're trying to maximize the correlation. And the one single difference between our network and a traditional network is that instead of using ReLU or sigmoid, we use the feature map of a Gaussian kernel as the activation function. In theory, you can use anything, but you have to do the analysis differently. But anyways, we use the Gaussian kernel because it's the standard kernel you use for like kernel networks. So as I was saying, AIStats actually turned out to be very ideal because it automatically finds the ideal similarity for us. And you can see that because the objective can be rewritten as this. And let me explain to you what this means. Now, when we're trying to maximize the objective with respect to W, what we are finding is we're finding a kernel. So W is defining a kernel. And when two samples are in the same class, S for same class, right? When two samples are in the same class, then when you maximize this, their relationship is going to get maximized. And when they're in different classes, it's as complement, then they're going to try to, because of the negative sign, they're going to try to minimize their relationship. So it's automatically finding the kernel that's maximizing the relationship of samples in the same class and minimizing relationship between samples in different classes. Hence, allowing us to automatically find the similarity measure. And the second thing why AIStat is so great is that we discover that when we maximize AIStat, it's actually minimizing MSE and cross entropy simultaneously in some kind of geometric it's alignment. So geometrically, it's minimizing them, and therefore we didn't really have to choose between AIStat, MSE, or cross entropy. They're they're actually essentially the same. Where AIStat is less restrictive, where f of x doesn't have to be the label. That's really the only difference. So here's our claim. Now, if at each layer we're trying to maximize the AIStat, right? Each layer we're trying to maximize. If we use the kernel mean embedding of RL1, and we plug that into the weight, that's all we have to do. Here's the kernel mean embedding. The network automatically maximizes. Now, let me take a second and explain the kernel mean embedding. So, the kernel mean embedding will take this value and form this matrix. Now, this 1 here means all the samples from class 1, all the samples in class 2. So you map it here, and you just take the average of all the samples of class 1, and that becomes the first column of this. And then the average of all the samples of class 2 becomes the second column. So if you have two classes, then that's it. Just 2 columns, and that's what the weight becomes. That's basically really simple. And this discovery is based on our theoretical result of the following theorem. We essentially show that the objective at layer L can approach arbitrarily close to the global optimum. So this is the global optimum, right? We can get as close to the global optimum as we want, given the existence of some kind of gamma value for the Gaussian kernel. And this is very interesting because as long as L is greater than 1, and this implies that as long as the network depth is 2, you can achieve the global optimum. That's the minimum amount. Of course, you want it deeper. We found that when you use very only 2 layers, then the sigma value becomes very small, and you don't want that. But it's theoretically possible to just use 2 layers. And second, that if you were to keep stacking it, it's guaranteed to approach the global optimum. And third, we know that it's guaranteed that given the existence of some kind of sigma, it's guaranteed that your objective is monotonically increasing. So it's always getting better and better until it reaches the global optimum. So we ran some experiments on this objective. And first experiment is that we have to generate some random data in 2D, and we give a random label. So it doesn't get more random than that. And we want to know that even with completely random data, can we approach the global optimum? So then we pass this data through the network and project the output to like 1 dimension. So each one of these is at the 1 dimension of a single layer. And you can see that in the beginning, the 2 classes, circle and cross, are basically mixed together. But as you add more and more layers, as you're improving the network, by the time you get to the layer 9, you can see a clear separation between the cross and the circle. And then as you increase more layers, the separation becomes bigger until you get to the 12th layer. Essentially, all the samples that are in the same class are just on top of each other. And all the samples on same class on top, and they are pushed apart from other classes as much as possible. And the second experiment we ran said, well, what if we even make it harder, right? Well, let's make it adversarial so that samples in different classes are practically on top of each other. Can we still train the network? So we follow through. In the beginning, you can see them mixed together, but actually, surprisingly, very quickly you see a separation. And then here is yet another separation. And similarly, at around layer 12, the samples that are in the same class are practically on top of each other and as far as possible from samples of different classes. So this right here is an experiment that confirms our theoretical claim. In claim 2, we say that, as I was saying, we want to know if we keep adding network, the network is going to converge. And it turns out that if you keep looking at the output after the activation, output again, this right here forms a kernel where, well, it forms the feature map of a kernel where the kernel is defined as this. So here's the definition of a kernel. If two samples are in the same class, right, xi, xj, you put two samples. If they're in the same class, this kernel is going to give you 1. And if two samples are in different classes, this sample is going to give you 0. Okay, so this right here is essentially an indicator function that tells you if two samples simply belong in the same class or not. And it turns out that as you add more and more layers, this converges to this kernel, and we call this kernel the Neural Indicator Kernel because it's like an indication function. Now, I note that this is after the activation function. We also study what happens before the activation function, right here, right before the activation function. Well, again, samples in the same class, we can measure the distance between them. And samples in different classes, we can also measure the distance between them. What happened is that the trace ratio approaches 0. What does that mean? It means that samples in the same class, the distance between them approaches 0, while the distance between them gets very, very large. And this is what's happening right before. And these claims are backed by theorem 2 of our paper, which says that, well, the trace ratio approaches 0, and that the kernel sequence converges to the neural indicator kernel. Here we go. And we actually ran some experiments to visually see this. You can see that in the first layer, the samples are basically looking the same as regular. But as soon as we reach second layer, you start seeing the clustering, the clumping of samples into a single point. And it gets smaller and smaller. So it eventually gets to a point that it's just a single dot. So you can see this trace ratio in action. As for the kernel, you can see that in the first layer, there's not much relationship. But samples in the same class are going to give you 1, and sample in different classes will give you 0. So the more white it is closer to 0. And you can see by the fourth layer, essentially samples of the same are going to give you very close to 1. And then it's basically white all around. Hence, confirming, actually visualizing what the formation of the neural indicator kernel. Claim number 4, I already talked about it, that when we maximize AIStats, it actually implicitly minimizes cross entropy and mean square error, right? So we're going to refer mean square error and cross entropy as label matching objectives. And AIStats is actually a non-label matching objective. It doesn't match the label. It actually just matches the geometric orientation. And you will have to read the proof on what we mean by that. And another implication is that since we're using the kernel mean embedding, what is happening is that we're really just finding the kernel density estimation. So we're computing the most likely classes and essentially reaching the base optimal classifier. Now, this was not in the paper, so I think maybe a separate explanation is required for this. Now, the implication 3 goes back to like the neural network implication that like, hey, we can just use like very simple and repetitive patterns and we can achieve universality, implying that we can classify any pattern. Like all we have to do is basically repeat it over and over again. And perhaps we're not saying this is the case, but perhaps we can look into this possibility for the brain that what we have shown is that you can use very simple patterns, yet able to classify and generalize on very complicated data. And here are the 2 corollaries that we found. Now, another interesting thing we discovered was that when we add the weights, traditionally when you do layer-wise network, you maximize the weight at each layer separately. And what we discover is that when we use the kernel mean embedding, this is actually not the local optimal. Like what we are saying is that you don't really care. It doesn't matter if you maximize each layer. As long as the entire pattern allows you to approach the global optimal, that's all that matters. And this is a different paradigm than how layer-wise network has been trained. And basically literally maximizing each layer separately. And we are not doing that anymore. However, out of curiosity, we were thinking, well, what if we do maximize this objective, right? And if we were to look at each layer as the actual objective, this will become the objective function. This is the AIStat objective, yet written differently. Now, because of the Stiefel manifold, we have a very, very complicated objective, and the constraint is on a sphere. So you have to find the optimal location that simultaneously intersects with the ball. And we were able to find, like interestingly, that the optimal solution is actually the eigenvector, the most dominant eigenvector of this matrix. So you can find it. So we were thinking, okay, so now we have 2 separate solutions. One is more interesting because it's a closed form solution. Other one is more from an optimization perspective, which you use the optimal solution here. And we did study the difference between them. And it turns out that W does converge, that the optimal solution does converge faster and does generalize better, which makes sense. But you do have to calculate it, and therefore not a closed form solution. But at this point, it leads us to a very interesting generalization question. Since our network is infinitely wide, shouldn't it, based on classical learning theory, shouldn't it overfit? And this is a similar problem that neural network have traditionally. Traditionally, neural network notice that even though they are over-parameterized, they still generalize. And we have a similar problem. And I want to get to the bottom of why. Even though I didn't use a regularizer, it somehow like regularizes. So what we discover is that this the AIStat objective actually implicitly regularizes. And you can see that is that we can yet again rewrite the AIStat objective. And when we rewrite it this way, a regularizer pops up. So the answer here is actually pretty obvious. It's not that it's generalizing without a regularizer. Instead, the regularizer is actually built directly into AIStat, where the regularizer actually becomes stronger and stronger the more you optimize. You will have to read the paper for detail on this, but this is not a single constant regularizer. This is a changing regularizer whereas you get a better solution, the regularization gets stronger and stronger and stronger. And therefore, this is a very strong regularizer. And it explains why you don't need a regularizer and you can still have infinitely wide network and yet it generalizes, essentially for the AIStat objective. And lastly, we compare our network essentially to the traditional like multi-layer perceptron trained with stochastic gradient descent. And we're able to show that on the training data and the test data that like these are random, so they're supposed to do bad. But on the actual data set, you can see that they perform very, very close to each other. They're all very, very close to the same of getting the same result. And the difference is that we don't need to calculate it, like calculate gradient descent. We don't need to calculate gradients. We just calculate the weights directly. That's the difference. And yet we can approach very, very similar results. In fact, in some cases, notice in this one, we actually generalize better, right? This is a high dimension data. And we generalize, we got, especially this one, you got like very close to 100%. Whereas when you use cross entropy or mean square error, it didn't generalize as well. And that was like very interesting. And we know why it generalizes because it has a very strong regularizer. And what is interesting is obviously time, right? Since we don't have to do optimization, notice the difference in time. It took us, for like this one, for example, less than a second. And yet, for this network, it took 456 seconds, and this network, 11 seconds. Regardless, either one is a huge difference. And that's obvious because we don't need to run gradient descent and backpropagation. Now, for the rest of these, it's not as important. Basically, we can show that we can essentially approach the global optimum regardless. So this is essentially our research for the past 3 years, and this is what we discovered. Now, these are the authors. My name is Chieh Wu, like I said. This is me right here, a good-looking guy. I'm at Northeastern University. And my co-first author, his name is Aria. He's about to graduate soon. Our advisor's name is Jennifer. And my second advisor's name is author Gretton. So I want to give special thanks to all the authors. We've put a lot of work into this. And here is essentially some of my publication, things that I have done in the past. I thank you so much. I thank you so much for watching this video. And hopefully I'll run into you at AIStats. You're welcome to come and stop by. Ask me some questions if you want to meet me in person. Thank you.